All right, so in this last lecture for this chapter, we're actually going to meet the final statistic that's going to help us to understand whether or not our results were significant. So we've talked a little bit about within groups variability, and we've talked about between groups variability. Remember, within groups variability is our closest measure of error that we have in our two-group or multiple group experiment. This is how people within a single treatment group vary from one another. In other words, people getting the exact same treatment or manipulation still differ in their scores on a dependent variable. This we can't explain, so we call it error. Next, the between groups variability. This is how people, on average, within a single group, getting one kind of treatment, like drug A, differ from people in a second group, on average, getting a different treatment, like drug B or a control. The differences between these groups may also be due to error, but they may be due to the kinds of treatment we're giving them. For instance, drug A versus drug B versus drug C. What we need to be able to do to see whether or not the differences between our groups are bigger than we would expect by chance is we need to compare these types of variance. We compare between group variance to within group variance. And what we want to know is, are the differences between groups due to more than random error? If the treatment did have an effect, then our between group variance, which is our error plus treatment, should be bigger than our within group variance. In other words, drug A should be different enough from the control group that it's bigger than we would expect by chance alone. That difference is bigger than we would expect by chance alone. So let's link that back in with the visuals that we talked about. Remember, this is how we represented three people in receiving drug A, three people receiving drug B, and three people receiving a control or no drug at all. These are what we called our observations. Now, even within a single group like group A, these people, we want to say that this group who received drug A is meaningful in some way. In other words, we want to be able to explain all three of these scores by using a single value or a mean value. So that's what we did. We calculated the mean value. This is our expectation for what the average person getting drug A would be like, both in our study as well as in the real world. We have the same thing for group B and the same thing for the control group. Now, what we're asking with our analysis is, first, how much error is involved in this study? In other words, people within a single group, like group A, are still going to differ from that group mean score. So drug A is obviously not explaining all of their levels of happiness, because we still have some people in this group who are scoring higher than the group average in happiness and some low. These variances is what we call error variance, and we have it for each one of the groups, drug group B and the control group as well. Next, we want to compare those variances to the variability that we see between each one of the groups. Let me erase this. Between each one of the groups and the grand mean, or what we've called the null expectation. In other words, if these groups are really no different from one another, if the drug doesn't do anything to happiness levels, we would expect all of these means to be approximately equal to the grand mean. And so what we need to do is compare what is the difference between groups, the between group variance, between the control group and this grand mean, between drug group A and the grand mean, and between this and the grand mean, although those are identical here. Once we have that between group variance, we're going to then compare it to the within group variance, the error variance. And to do this, we use the F statistic. Now, technically, this is calculated by comparing the mean squares of the treatment, or MS between. This is really our between groups variance, comparing that to the within group treatment, the mean squares of the error, or the MS within, or within group. These are the two types of variance that we just saw. Another way to refer to these is by virtue of what affects them. So remember, the mean squares for the treatment we've suggested is due in part to random error, because we always have random error, but it may also be due to our treatment, the drug that a person gets, pushing their happiness either higher or lower. Whereas the mean squares within, or the mean squares error, is always due to random error, things that we haven't controlled or manipulated in our study. Okay, so I'm going to erase this for a second. And now I want to ask you to think about this question and to try to respond in the text box below with your best answer. Why is it that an f of 1, so each one of these is a ratio. You divide what's on top by what's on bottom. If you were to divide mean squares treatment by mean squares error, you get a number. Why is it that an f of 1 does not show that the treatment had an effect? Take your best shot at explaining this in a sentence or two. Imagine that your grandma was asking you, what did you learn today about statistics and the F statistic? And you have to try to explain why an f of 1 does not show that the treatment had an effect. Take your best shot. Write 2 or 3 sentences. Even if they're terrible, even if you say, I have no idea what's going on, write them, you'll get credit for it. But I want to see kind of how much you're getting it at this point. When you're done, come back to the video. Okay, an f of 1 does not show that the treatment had an effect because what this means is, let's say, the amount of variance up top, let's just imagine that was the number 3, is equal to the amount of variance on the bottom. An f of 1 is always equal to the same thing on top as on bottom, right? These are ratios that equal 1. So what this means is that the random, if we had the number 3, for instance, I just picked that number randomly. If we had the number 3, what that means is random error plus treatment gives us 3 units of variability. Random error alone gives us 3 units of variability. So if we know that this random error, or that this between groups variance is due to random error and perhaps treatment, what we see is really we have the same amount on top as on the bottom. We know we have random error, and so an f of 1 tells us really all we have on the top and on the bottom is the same thing. So we say we have the same amount of random error on top as we do on the bottom and nothing else. In other words, there's no treatment because this number isn't any bigger. Numbers bigger than 1, so like if we had a 6 over 3, that f would equal 2. 6 over 3 equals 2. This would tell us that there is on top certainly the random error that we see on the bottom, but also more. So that 6 has to be equal to the random error that we see on the bottom plus variability due to the treatment, some other number. So we know our treatment, or we suspect our treatment had an effect. So to see if the f is significantly above 1, what we do is we use an f table. First of all, we choose a significance level. Now, in the field of psychology, we typically, and I'm always going to have you guys choose a significance value of p is less than 0.05. What that means, and we'll talk more about this in class, is that 5% of the time, we are going to accidentally say something is real, some difference is real, when in fact it's not. But 95% of the time, when we see 2 mean scores, like drug group A and a control, that are different at a p is less than 0.05 level, what we're saying is 95% of the time means that are that different are not that different due to chance. Or another way of saying that is, if chance alone, a random person in this group versus this group that could have gotten placed somewhere else, if chance alone is driving these differences, then we'll only see group means this different 5% of the time. So we choose our significance level. Next, we're going to look under the correct degrees of freedom. I'll show you an F table in a couple slides. So here's the first time I'm introducing this idea of degrees of freedom. For right now, I'll explain more later what a degree of freedom is. But right now, what you need to know is just how to calculate it. So for an F table, the degrees of freedom for our treatment, think about this as groups. Each group is getting a different kind of treatment. The degrees of freedom for treatment is simply the number of groups minus 1. Groups minus 1. So our DF equals groups minus 1. If we have 3 groups, then 3 minus 1, number of groups 3 minus 1 equals a degree of freedom of 2 for our treatment. The second degree of freedom is called degrees of freedom error, or sometimes called DF within groups. Now for this, what we want to know, the way that we calculate out this degree of freedom is we take the total number of participants in our study. So let's say for our earlier study, drug A, drug B, drug C, we had 3 people in each group, which led to a total of 9 participants. And we had 3 groups, drug A, drug B, drug C. So our degrees of freedom for our previous experiment would have been 9 people minus 3 groups equals 6. So our DF within, or our degrees of freedom error, is 6. Now the way that you'll oftentimes see this written, and when you'll write it up in your statistical reports, is you write the letter F, because we're looking for an F value, and then degrees of freedom 1, or degrees of freedom treatment, comma, degrees of freedom error. So here for our study, we would write F, degrees of freedom treatment is 2, degrees of freedom error is 6, equals, and then whatever our value is. So if we had an F of 2.0, we'd write it like, actually we usually do to 2 decimal places. So F26 equals 2.0. F with the degrees of freedom between of 2 and within of 6 equals 2.0. And then we're going to take a look and use the F table. So for right now, I'm going to give you I'll give you a slightly different F value. So let's do this one. F of 2, 6. So here on this F table, along the top, we're always going to have the degrees of freedom for treatment listed. And along the side, we have the degrees of freedom for error listed. So to find out if our F here, our F equals 3.27, we need to compare that F with another one of these F values in this F table. To find which F value we're going to use, we have to use these degrees of freedom. So I want you to pause the video, see if you can figure out which F we compare our value to, which of these many values on the table we're going to use to compare our F to. Write it down, and then come back into the video. Don't worry if you get it wrong. Don't correct it. If you get it wrong, you get credit just for listing it. Okay. So do that, and then unpause the video. Okay. So in this, what we first have to ask is, what's the degrees of freedom treatment? And our degrees of freedom treatment is 2. So we take a look at the degrees of freedom treatment on the top, and we find 2 over here. What's our degrees of freedom error, or within? That's 6. So now we have to look over on this side, on the left side, for our degrees of freedom error. So we find degrees of freedom 6 right here. Now we find our F critical value, this is what we're going to call it, by going over to our 2 and then down to our 6. So we go down and over, and what we find is our F critical value is 5.14. So what we need to do in order to tell whether or not our F is significant is we have to compare our value of 3.27 to this F critical value. Now, there's lots of ways to think about this. What I want to encourage you to think about it is the critical value that's listed on a table. Think about this like a hurdle. And our F value has to jump over this hurdle. Our F value needs to be bigger than the F critical value. So what we see is 3.27 versus 5.14. We need it to be bigger than our critical value, but it's not. It's less than. So this F is not significant. Our F value of 3.27 was not bigger than our F critical value. Okay, the next thing I want to ask you is, just looking at this F, let me erase this again. Just looking at this F value down here, how many groups were there in this study? And actually, I'll ask you another question. How many participants were there? Pause the video and jot down below how many groups you think there were and how many participants you think there were. Okay, this one is a little bit more straightforward because we came up with the exact same degrees of freedom before. Here, if our degrees of freedom between is 2, remember, df between equals the number of groups minus 1. Well, if that equals 2, then we know groups minus 1 equals 2. So groups of 3, groups have to equal 3 because 3 minus 1 equals 2. How many participants were there? Well, now if we know that there were 3 groups, df within, or df error, equals total number of participants minus the total number of groups. Well, if we know that there were 3 groups in this study, n minus 3, both of these have to equal 6 over here. So we see, take this value of 6, put it right there. We know that has to equal 6. So if n minus 3 equals 6, we know that n is 9. 9 minus 3 equals 6. So we know that there were 9 participants and 3 groups in this study. Okay, so let's check that out one more time. Try it again. So here, remember, looking at an ANOVA table, when your F value is shown, you can tell 2 things about an experiment. One, you can tell the number of levels of a treatment. We've called this the number of groups. So in our 3-group study, we had 3 levels of the drug treatment. Drug A, drug B, and control. 3 levels. The way that you find that out is you take your degrees of freedom treatment plus 1. So back here, we had our degrees of freedom treatment was 2. All we have to do is add 1, 2 plus 1, and we get 3 groups. Okay. The second thing that we can tell is the number of participants. There's a couple different ways we can do that. One, we can use the DF total, which we haven't talked about. But second, we can use the degrees of freedom error plus the number of levels or groups, which we've just figured out up here, plus 1. Okay, those are all things that we just did before. The DF error plus the levels of group plus 1. So let's take a look at this study right here. Here are the results. And this is how we might write up the ANOVA summary table for this. So right here, I've taken out all the sums of squares because we don't need to use them. Let's imagine that this was the summary table. And one of the things that a summary table will tell us is it will tell us the degrees of freedom. Degrees of freedom between is 2, within is 6, and the total degrees of freedom is 8. This is exactly the same that we saw for our example before. So to find out how many groups there are, we add 1 to this, and we have 3 groups. For our within group error, to find the number of participants, we add the numbers of groups plus 1, which gives us, degrees of freedom groups, degrees of freedom plus the number of levels of groups. My bad on that. Plus 3. Take out that plus 1. So 6 plus 3 gives us 9. Okay. So let's do this for one more example here. Let's imagine this is what your degrees of freedom, what your summary table looks like. I want you to pause the video and try to answer both of these questions. For this study, how many groups were used and how many participants were there? Unpause the video when you're done. Okay, to find the number of groups, we take the degrees of freedom between and we simply add 1. What we find is there were 4 groups. To find the number of participants, there's 2 ways of doing that. One of them is to take the degrees of freedom within and add the number of groups, 4, which gives us 30 participants. The other way to do that is to take the degrees of freedom total and simply add 1, which also gives us 30 participants. So this is a really quick way that when you see an ANOVA table in an article, you can look at that table and immediately know how many groups did they compare, 3 plus 1, and how many participants were used. Degrees of freedom total plus 1. Okay, so the last concluding remark that I just want to say is why is it that we would use multiple groups experiments? Well, one, if we want to compare multiple different treatments to one another, so drug A versus drug B. Sometimes we want to do it to increase external validity. We want to give a drug in a hospital setting and a drug in a doctor's office and a drug that you receive through the mail and see if they all work equally well. Sometimes we want to do it to increase construct validity. So for instance, we want to see, is this really the drug or is it people's expectations about the drug? So we want to differentiate the drug itself from how people feel about a drug. And so to do that, we might use a placebo control group versus an empty control group. Why know about how to analyze these kind of experiments? Well, for the most part, for you guys, it's because you're going to have to read the results of these kinds of studies, both in this class, but also in other classes, and eventually, hopefully, in your life afterwards. For some of you, it's because you're actually going to design these kinds of studies. This is a part of what you have done in this class, is to design a study like this. And for some of you guys, it may be, well, all of you in this class, it's so you can analyze the results of the studies that you conduct. Okay, so that's it for today. When we come into class, what we're going to do is a few different class exercises around these